Okay, the second of Kirchhoff's laws is his voltage law. So what does the voltage law say? So this one's a bit more involved. It says, around a circuit, or around a closed loop in a circuit, the sum of the EMFs which is the potential difference increase due to a cell, equals the sum of potential differences around that loop. Or, in other words, in the absence of any EMFs, in the absence of any cells, sum of all potential differences equals 0. Okay, so what does this actually mean? Well, the best way to do this is to actually look at some examples. So, what we need to do firstly is to find some closed loops. So, let's take firstly, I'm going to do this in green, this loop here. So just because there's this other branch in the middle, that makes no difference. Any closed loop we can apply this to. So here, what can we say? Well, I've got an EMF due to this cell at the top. Okay. So let's call that V in. Now notice the arrow I've used, that's to show the direction that we're going. Now what we're going to do now is we're going to follow this loop around this direction. So we're going to go anti-clockwise. So following this loop around, we're looking for any sources of EMF or potential difference. So if I follow this round, nothing so far, I've just got the wire. So now we have a resistor here. So here, this resistor is going to have a potential difference across it. So let's call that V1. So if I keep following this around, we get back to the start. So, what does Kirchhoff's law say? So it says for this green loop, let's stick with green, sum of the EMFs equals sum of the potential differences. So here, what have we got? Well, my EMFs, well, I've only got the one, which is V in. My potential differences, well, I've only got the one. So we can say that V1 equals V in. Okay, well, let's take another example now. Let's change colour. We've got a second closed loop, so let's look at this one now. Following this one around, we've got this orange loop. So let's follow that around and have a little look. So starting from the cell again, we've got an EMF, so let's get that in now. V in equals, following this around anti-clockwise again. Okay, well, we get to a resistor here. So that's going to have a potential difference across it. Let's call it V2. Let's keep going. I get to another resistor, which has a resistance V3. Okay, so we can say that the sum of my potential differences, are V2 plus V3. So I've got another equation here. Okay, we're not done yet. There's a third closed loop we can look at. So I'll do this in purple. So this bottom loop here, we can also apply Kirchhoff's voltage laws to. So we'll go around it in the same direction, and we'll start here this time. So going around anti-clockwise, well, in this case, we can see we're going to have 0 EMFs. So let's put 0 there, equals. Here, I've got V1. Following this around, this purple loop, Okay, I get to V3 here, but I've deliberately drawn an arrow to show the direction at which the potential difference drop is. Now I'm going against that arrow, so that means I'm going to have to have minus V3 because I'm going in the opposite direction. Similarly here, I get to V2, I'm also going to have a negative sign there. So what's this going to give me? Well, that basically says V1 equals V2 plus V3. So I've got another equation here. So basically, what I've shown is that in parallel, voltage across branches is the same. So the two branches in my parallel circuit, this branch and this branch, have the same total voltage across them. So let's put some numbers to this and see if we can actually work this out. Okay, so looking at this circuit, I've got a parallel circuit with a few unknowns in it. So we're using Kirchhoff's voltage law. So let's start with this closed loop down the bottom. Nice big one around the outside. So, over here, we can say sum of EMFs equals sum of potential differences. So, let's start here. Well, I've got a 12 volt cell here. As I follow this round, no potential differences, and now I get to this voltage here. Okay, so I could call this V1, but what do I know about it? Well, I can be clever with this. I can say, well, I've got a 12 ohm resistor, and I've got a current I3 going through it. So I can use this equation to say, okay, well, V1 is going to equal 12I3. So I'm going to say 12I3 here. So now I've got an algebraic equation. Well, with a bit of rearranging, we can therefore work out that I3 is going to equal 1 amp. So this current here will equal 1 amp. Okay, well, let's keep going. Let's think about another loop. Let's do this one in pink. So we did that bottom resistor. Well, let's pick this route now. So as before, we're going to follow around the loop. We've got a 12 volt cell again. Well, let's follow this around. So here we're going to get to another resistor. Well, we don't know what this one is. We've got two unknowns. Well, we can say my current is going to be I2. My resistance is R. So the potential difference across that resistor will be I2R. Well, let's keep going. Here, another resistor. What's the potential difference across it? Well, it's going to be V3, which we could say will be I2 times 10. So, 10I2. Good, so we're getting somewhere, and there's no more sources of EMF in that circuit. All right, well, let's just simplify that equation a little bit, just to tidy it up. R plus 10 equals 12. Okay, so we've got two unknowns there. So how are we going to proceed from here? Well, let's have a little think. We can use our third. There's a couple of ways we could go from here. But let's stick with the current law, and let's look at this one. Sorry, the voltage law. Okay, so let's go. Stick with the same direction, this way around the circuit. Sum of my EMFs equals sum of my potential differences. Well, here we can see 0 EMFs. So let's follow this around. V1, this resistor, what are we going to get to here? Well, we know that I've got 12 12I3. And so my potential difference across this one will be 12 volts, because I3 equals 1. Okay, let's keep going around here. So now we get to this resistor. Remembering, I'm going against that arrow, so I'm going to have minus 10I2. Keep going. I've got this other resistor, so it's again going to be a minus sign, minus R times I2. So now we have a little equation. 12 equals I2 R plus 10. So that is actually exactly the same as the one in pink. So where can we go from here? We've hit a bit of a roadblock. We've got two unknowns. How are we going to solve it? So we need to be clever here. Let's go back to our current law. You might have spotted this already. And let's pick a junction. Well, we know that sum of currents in equals sum of currents out. Well, we've got 1.6 amps going in equals I2 plus I3. Well, we already worked out I2, which equals 1 amp. Therefore, I3 equals, excuse me, got those the wrong way round. I2 equals 0.6. Once we've got that, then we can substitute that in and use this to solve our value for R. So let's substitute that into here. 12 equals 0.6 R plus 10. So, how can we solve this? Well, let's expand out that bracket. So, 6 equals 0.6 R. So 6 divided by 0.6 equals 10, which equals the value of my unknown resistance. So this resistor here will have a resistance of 10 ohms. Okay, so this, again, just as before, we've got this tricky looking circuit. Can we apply Kirchhoff's laws to help us solve some difficult questions? So this question in red, what is the potential difference across this thermistor? How are we going to work that out? Well, we need to look for some closed loops. So simplest one would be this guy here. Okay, so let's have a little go at following this round. Well, we've got a potential difference of 5 volts across this resistor. So let's follow my loop around. So we've got no EMFs in this circuit, so we can say sum of potential differences equals 0. So we've got 5 volts, and let's say I've got, let's call that V. So 5 volts, I'm trying to go into that to save confusion, 5 plus V. The ammeter is ideal, so it has no potential difference across it, equals 0. Well, where do we go from here? Well, a bit of rearranging, that tells me that V equals minus 5. What does that actually mean, minus 5 volts across it? Well, that means I've got the arrow the wrong way around. My potential difference will actually be 5 volts that way. So, that's going to be the potential difference across that thermistor. Well, what about the second question now? The bottom bulb, this guy here. How are we going to work this one out? Again, we need to find a closed loop. So let's pick this loop here. So what I'm looking for is the potential difference across this guy here. So I've drawn my arrow on, just as we saw before. If I've put it in the wrong direction, it doesn't matter, I'll just end up with a minus sign at the end. So I'm going to follow this around anti-clockwise, just because it makes it easier for the cell. I do have an EMF in this case of 1 volt. equals, well, let's look at my potential differences. Here, I'm going in the same direction as that arrow, so I've got a voltage of V. Potential difference across this resistor, same direction as that arrow, plus 1. And I've got another potential difference here going in the opposite direction, so that's going to be minus 3 there. Okay, so there's my closed loop. Let's tidy this up. 1 equals V minus 2, so V equals 3 volts. I didn't end up with a minus sign, so I must be in the right direction. So that value there will equal 3 volts. Good. So, well, let's have a go at a final question, just to make sure we're very happy with this. Kirchhoff's laws are applied to the circuit shown. So this is an actual exam question. What is the equation for the dotted loop? So reading into this, straight away I'm thinking, okay, we're talking about a loop, so that means we must be using Kirchhoff's voltage law. So, depending which way round we're going, well, let's just pick this one here. So here, we've got no EMFs in this loop. So my sum of my potential differences will equal 0. Well, here, what's the voltage across this guy? Well, it's going to be V equals IR, so it's going to be I2 times 3. Okay, let's keep going around. And now, well, if we look at the direction that that current I3 is going, I'm going to have another voltage going that direction. So what's the current here? Well, because I'm going against that blue arrow, I'm now going to have that minus sign in there. I'm going to end up with minus 4I3. Okay. So this is my equation using Kirchhoff's voltage law around that closed loop. Let's have a little look at the possible answers. Well, I know if I'm looking at this circuit, well, these two here, well, that's in there to trick you. We've got this 6 volts, which is up here. That's not in my loop. That's not relevant. So straight away, I can get rid of those two. Of the other two, well, this one here, this one's in there to catch you out, to see if you've spotted that you're going against the current in one direction. This version here is just a rearranged version of mine, so we're going to end up with B as our final answer.